Continuing with our look at rates of change, and we can talk about integration as well. Because remember, this is what integration will allow us to do. If we know the rate of change, then we can integrate and get back to some equation for the original quantity that we're investigating. 2017 this one comes from. So water is flowing into a tank. There's our rate of change. V to t is 2t or 1 plus t squared. V is volume, t is time. How much water is in the tank after 10 seconds, basically, is what's being asked. Okay, there's our V to t. I personally think the simplest way of doing this is doing it as a definite integral. And so when we're doing that with something like this, we what's called separate the variables. And we'll look at separation of the variables in a little bit more detail when we see this topic of differential equations. But basically what we're saying is I want to rearrange this so that on each side of the equal sign are the two different variables. I've separated them. One variable goes to one side, one variable goes to the other. But when I do that separation, I also add in an integral sign. So we end up with this. Basically the only thing that has to move is the bottom of this fraction, the t. So the t ends up going to the other side. And I end up with the integral of dv is the integral of 2t on 1 plus t squared. Now as far as the limits go, we then match the limits. So they gave us some information, and that information was somewhere, well, they haven't explicitly said it, but we can assume that when t equals 0 there is no water in the tank, because water is flowing into a tank. So I've said, well, when t equals 0, the volume is 0, we want to find what happens when t is 10. So I'll put t is 10, I want to find out what v is. This is now the problem I have to solve. So okay, integral of v is just v, and on the right hand side we have a little log of 1 plus t squared. Substitute in, and it drops out quite nicely. We just get v as the log of 101. So there's our answer. Log of 101 litres of water left in our tank. We have an acceleration time function this time. So x is displacement, t is time, and so on. Initially, we're at the origin, velocity is 1. When does the particle first come to rest? Okay, well, acceleration is v to t, we know that. Again, I'll separate those variables out. Now, the initial conditions they told me this time was that when t equals 0, v is equal to 1. We want to know how long, so what is t when the velocity is 0. The left-hand side just becomes v, right-hand side integrate cos, we get sine. So -1 is 2 sine 2t. We've got ourselves a trig equation to solve. Now, of course, there are infinite number of answers to a trig equation because it goes round and round and round. But they've told us the first time. So the first time this would be 0, and we're assuming t will be positive, it would be 7 pi on 6. So when we divide by 2, we get 7 pi on 12. So it comes to rest after 7 pi on 12 seconds. One from last year's HSC. So a camera films the motion of a swing, and x is the horizontal distance of that swing, and it starts from a distance of 11.2 meters, right? Hey? And they've given us the equation there, dx to t is that. Find an expression for the displacement. Well, there's dx to t, separate out the variables. They told us when t is 0, displacement was 11.2, and this time I've got variables on both of them because we're trying to find an equation. I want to know what is x when at time t. Left hand side is just x, right hand side, integrate sine, we get negative cos. So x minus 11.2 is my right hand side, move the 11.2 over, and we have an equation. A spherical raindrop, radius r, loses water through evaporation at a rate depends upon its surface area. So there it is, v to t is minus 10 to the power of -4 times the surface area. T is in seconds, yeah. Show that dr to t is a constant. Okay, so we want dr to t. We have dv to t. So can we link velocity and radius together? That's ideally what we'd like to do here. Well, yes. Volume is 4/3 pi r cubed. There it is. Differentiate the volume, you get the surface area, 4 pi r squared. But in this case, I'm going to replace 4 pi r squared with a, because a is the surface area. This now, when I substitute in, the A's end up cancelling and I end up with that constant number. And that's what they wanted me to show that d/r to t is constant. We've done that. It is constant, and that constant rate is 10 to the negative 4 metres per second. How long does it take for a raindrop of volume 10 to the negative 6? Wow, that's small. Well, I suppose raindrops aren't that big, are they? Certainly when we're talking about metres cubed, to completely evaporate. So d/r to t we have just worked out is minus 10 to the power of negative 4. What I've now worked out is the initial radius, because that's what we're going to end up substituting into our formula. It's a lovely expression. The cubed root of 3 times 10 to the negative 6 divided by 4 pi. I'm not going to bother with the decimal approximation on that. I'll just leave it like that. All right, separate out the variables, and there's that lovely expression for the limit there. But then t, now, when you simply have 0 to t of the t, something like that, it's okay just to go, well, that's going to be t. Because go through what would happen, you'd integrate the dt and you'd get t. You're going to substitute in t for t, and then substitute in 0, which goes away. So that one we often just go, oh, well, that's t. The other side, though, I do need to put r there because we've got things to substitute in. And it'll be 10 to the power of 4 times the cube root of 3 times 10 to the negative 6 and so on. Now I'll go to my calculator, and to the nearest second, that's 62 seconds. So it's going to take about 62 seconds to evaporate. So carrying on with rates of change.